These are your notes for Unit 4, Day 2 of Pre-Calculus. If you would like to see the warm-up review question or any homework questions we covered in today's class, just look at the finish notes. So today we're going to talk a little bit more about polynomial functions and how to graph them by hand and how to graph them and build models using Desmos from data. So graphing polynomials. So some steps that you're going to want to take to graph polynomials by hand. So the first thing you can determine is the end behavior. So we talked about this. So the easiest way to think about it is x squared is an even polynomial and it has a positive leading coefficient. So his end behavior, the tails of the graph go up and up. If it's negative x squared, that's a sad parabola. So it's even and the leading coefficient is negative. So if the exponent is even, the degree is even, and the leading coefficient is negative, then the tails, the end behavior will go down and down. If it's positive and odd, so if it's a positive leading coefficient and the exponent is odd, it's the snake, and the end behavior starts down and ends up. And then if it's negative x cubed, so a negative leading coefficient and an odd exponent, the end behavior starts up and then ends down. So that's a review from last class, or maybe the class before. Then you want to find the x and the y intercepts of the graph. So remember, let x equal 0, solve for y. Let y equal 0 and solve for x. Or you're making a table, x is 0, y is 0. What would be the partners for those? Then you're going to want to find the real zeros of the function. So the real zeros are your x-intercepts. And you're going to want to find the multiplicity of those. So remember, if it was like x minus 2 squared, then you would have a 0 at x equals 2. But since it's squared, remember that means that it doesn't pass through the x-axis. It just bounces off the x-axis there. So if it's an even multiplicity, then that means it doesn't cross through the x-axis at that point. It just bounces off the x-axis at that point. Then you're going to want to talk about the turning points. And remember, the maximum number of turning points is going to be the degree minus 1. So it's the highest exponent minus 1. That would be the number of turning points. And then remember, turning points on the graph are the peaks and the valleys. They're the local mins and maxes. And then you are going to want to use those steps to try and sketch a graph of your polynomial function. So determine the end behavior, find any x and y intercepts, find the multiplicity of the x-intercepts or your zeros, and then talk about how many turning points the graph could have based on its degree. So let's look at an example. So we have f of x equals x minus 2 times x plus 3 squared times x minus 5. So to talk about its end behavior, we need to know its degree and its leading coefficient. To figure this out, we technically only need to multiply the biggest x's together. So order of operations says do exponents first. So that guy would create an x squared. That guy has an x and that guy has an x. So if I multiplied those all out, I would have an x to the 4th term. So the degree of this polynomial is 4, and it's a positive leading coefficient. So remember, positive leading coefficient and even degree means the end behavior is going to go up and up. So both tails of this graph should go up and up. Let's find our x-intercepts. So to find our x-intercepts, you're going to let y equal 0. So 0 equals x minus 2 times x plus 3 squared times x minus 5. So my x-intercepts are at 2, negative 3, and then that's a multiplicity of 2. So remember, that means that it's going to touch the x-axis there and then bounce off. And then I have another x-intercept at 5. So at 2, I have an x-intercept. At negative 3, I have an x-intercept. And at positive 5, I have an x-intercept. And then be careful at negative 3. I'm just going to box that because that means that's where it's going to bounce off of. It's not going to cross through there. Let's find our y-intercept. So to find a y-intercept, you let x equal 0. So y is going to equal 0 minus 2 times 0 plus 3 squared times 0 minus 5. So I get negative 2 times 9 times negative 5. So my y-intercept is going to be positive 90. Okay, so I'm going to go by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90. So you can label your y-axis however you want to so that it fits. So it's going to cross over the y-axis at 90. The multiplicity piece we have right here. So we know that at -3, it's going to bounce off the graph. It's not going to cross over there. And then 2 and 5 are normal x-intercepts. So we've got all of our pieces. So my end behavior on the left side of the graph, it's got to start up. And then I know it's going to bounce. So since it's going to hit the x-axis there, it's going to bounce back up. And then I know that it's got to hit somewhere at 90. I don't know exactly. But then it has to cross through the x-axis at 2, and then it's going to have to cross the x-axis at 5, and then it's going to have to end going up. Oh, we forgot to talk about the turning point. Since it's x to the 4th, the number of turning points, the most that it could have is 1 less than that. So the most turning points that this graph could have would be 4 minus 1, which is 3. So we have 3 turning points right here, and right here. So that would be a sketch of this graph. It's not perfect because I don't know exactly where it's going to hit, but let's check out how close we were on Desmos. So if I graph this, we have y equals x minus 2 times x plus 3 squared and then times x minus 5. And then, oops, y equals, there we go. So now, if I have this, so notice it goes all the way up to a height of 90. Oh, and that was exactly where it hit and then came back down. So it went down pretty low, but overall, our picture is pretty good. We just didn't go down far enough on the guy right here, but everybody else looks pretty decent. So that would be how we could sketch a picture of that polynomial. So we found its degree, we found its end behavior, we found its x and y intercepts, we found its turning points, and the multiplicity of the x-intercepts. So let's try this one. F of x equals 5x times x squared minus 4 times x plus 3. So again, this would be an x times an x squared times an x. So an x times an x squared times an x. So the degree of this one is also going to be 4. And it's 5x times all of those, so it's going to be a positive leading coefficient. So the end behavior will be up and up again. To find x-intercepts, we're going to let y be 0. So 0 equals 5x times x squared minus 4 times x plus 3. So either 5x is 0, x squared minus 4 is 0, or x plus 3 is 0. So either x is 0, x is plus and minus 2, or x is negative 3. All of those happen once. So I have an x-intercept at 0, negative 2, positive 2, and negative 3. And it's going to cross through at all of those places because all of them have a multiplicity of 1. To find the y-intercept, we're going to let x be 0. So y equals 5 times 0 times 0 squared minus 4 times 0 plus 3. So this would be 0 minus 4 times 3. So my y-intercept is negative 12. So I'm going to go by 2's, negative 2, negative 4, negative 6, negative 8, negative 10, negative 12. So it's going to cross the y-axis there. The number of turning points, since the degree is 4, the number of turning points can be 1 less than that. So I could have up to 3 turning points. I know the end behavior was up and up, so it's going to start up. And then it's going to have to come back through because it's going to cross through each of those x-intercepts. So it's going to cross, oops, that was bad. Wait a second. F of x, so we have 0, x squared minus 4, and 3. Why does it have 2 points there? So 0, oh, because it's 0 times everything. Same, it's definitely good. So the y-intercept is 0, not negative 12, because it's 0 times negative 4 times 3. So the y-intercept is 0, so we're still okay. So it starts up, and then it goes through that x-intercept, and then it's going to come back and go through that x-intercept and through there. So the tails end up and up. It has at most 3 turning points, so we have 3 turning points, and then it goes through each of those x-intercepts. So graphing and analyzing polynomials on Desmos. So obviously Desmos can graph all of these polynomials for us. So let's go ahead and graph this guy on Desmos. So y equals x to the third plus 2.48 x squared minus 4.3 155x plus 2.484406. So if we want to analyze this graph on Desmos, it has one x-intercept, and its one x-intercept is at the point negative 3.7910. It has its y-intercept at the point 2.484. It has two turning points. So it has a local max and a local min, so it has two turning points. Its degree was 3. So having two turning points makes sense, and it's an even coefficient, so it should start down and end up for its end behavior, and it does. And there we go. We can talk about where this graph is increasing, decreasing, where it has a local min, local max. So it has a local max right here. So it has a local max at the point negative 2.283, 13.363. And then it has a local min at that valley. So it has a local minimum or a relative minimum at the point 0.631. Where is this graph increasing? Well, it's climbing at the start. So it's climbing from negative infinity on the x-axis to negative 2.283 on the x-axis. And then it climbs again from the point 0.63 to infinity. Where is this graph falling? Where is it decreasing? Well, it's decreasing from the x values of negative 2.283 to 0.63. So again, we can use Desmos to graph and analyze polynomial functions, just like we did in our previous units. So you guys go ahead and graph this on Desmos and analyze it. So find its intercepts, find where it's increasing, decreasing, its turning points, its local mins and maxes, and you can check your work against the finished notes from today's class. All right, so using Desmos to create cubic functions of best fit. So let's go ahead and pull this up. So let's, just like we did before, we're going to enter in our table. So we'll make our table. So we have the point 0, 100. We have the point 5, 128.1. We have the point 10, 144. We have the point 13 and 153.5. We have 17 and 161.2. We have 18 and we have 162.6. We have 20 and 166.3. We have 23 and 178.9. And we have 25 and 190.2. And we have 27 and 221.8. So press the magnifying button. I don't know why this didn't show up. There they are. So there we go. So this is looking like a snake. So it's looking like a cubic function. So if we wanted to create a cubic of best fit, so we have y equals, and then normally it's ax squared plus bx plus c, but this time it's going to be ax cubed plus bx squared plus cx plus d. So we're going to add another coefficient, or another variable in this case, d, because we have more terms that we could have, because we have an x cubed, an x squared, an x, and a constant. So on Desmos, we're going to do y1 is approximately a x1 cubed plus b x1 squared plus c x1 plus d. And that's going to allow us to create a cubic of best fit. So let's go ahead and go down to 2. And we're going to do y, and then y1. And then the ABC, and then the approximately. Then ax1 cubed plus bx1 squared plus cx1, and then plus d. And then notice that is going to be our cubic of best fit. That's the cubic curve that would fit those points the best. So our cubic of best fit is going to be y equals, and then it's going to be 0.015459x cubed and then minus 0.595142x squared, and then plus 9.15017x, and then plus 98.4327. And that would be our cubic of best fit for that data set. So we have the number of textbooks in thousands versus cost in thousands of dollars. So this is going to be like your cost per textbook. So remember, slope is the change in y over the change in x. So in this case, it's going to be the money per textbook. So this formula, this cubic formula, tells you how much textbooks would cost in thousands, or if you bought 5,000, 10,000, 27 textbooks, how much would they cost in thousands of dollars? So that would be that cubic function. So let's go ahead and do the same thing for this one. So this is hours after midnight, and then the temperatures in Kansas City, Missouri on March 18th of 2018. So let's go ahead and draw the scatter plot and then find the average rate of change from 9 to noon. What is the average rate of change from 3 to 9? And then decide a function of best fit, linear, quadratic, or cubic. And then we're going to use that to predict the temperature at 5. And then we're going to figure out what the y-intercept would mean in this problem. All right, so let's go ahead and start by making our scatter plot on Desmos. So let's erase this one, and let's erase this one. And then we'll make a table. And so we have 3 and 42.1. And we have 6 and 41.3. And we have 9 and 41. And we have 12 and 43.1. And we have 15 and 48.9. And we have 18 and 50. And we have 21 and 45. And we have 24 and 44.1. So there's our scatter plot. Ooh, that's an interesting looking scatter plot. So there's our scatter plot. We did it on Desmos. Find the average rate of change from 9 a.m. to noon. So these are hours after midnight. So if midnight, x would be 0. So 3 hours after midnight, this would be 3 a.m. This would be 6 a.m. This would be 9 a.m. This would be noon. 3 hours after noon would be 3 p.m. 6 hours after noon would be 6 p.m. This is 9 p.m. And then this is going to be midnight of the next day. Okay, so that's what those times, they're hours after midnight. So if you're 3 hours after midnight, you're 3 a.m. and so on and so forth. So the average rate of change from 9 a.m. to noon. Average rate of change, remember, is just your fancy way of saying slope. So the average rate of change is going to be the change in the y values over the change in the x values. Well, my y values are 43.1 minus 41 over my x values were 12 minus 9. So change in y over change in x would be my average rate of change. And so 43.1 minus 41 would be 2.1. And then 12 minus 3 is 3. So it's 2.1 over 3, or we can't have decimals and fractions. So this would be 21 over 30, which would be 7/10. So the average rate of change of the temperature from 9 a.m. to noon would be 0.7, and then remember it's change in y over change in x. The y values are degrees Fahrenheit, and the x value are in hours after midnight. So this is going to be 0.7 degrees Fahrenheit per hour. So between 9 and noon, the temperature was increasing about 0.7 degrees per hour. What's the average rate of change between 3 p.m. to 9 p.m.? So 3 p.m. to 9 p.m., I'm going to be 3 p.m. here and 9 p.m. here. So I'm finding the average rate of change between those points. And so that would be the change in the y over the change in the x. My y value at 9 p.m. was 45. My y value at 3 p.m. was 48.9. And then over 21 minus 15. Those would be the x values that correspond to 9 p.m. and 3 p.m. So this is going to be 45 minus 48.9 is negative 3.9 over 21 minus 15 is 7. So if I found I could leave it like that. So that means that my rate of change would, or my slope would be negative 3.9 over 7. So my average rate of change, if I actually want to know what that would be exactly, I am going to take negative 3.9 divided by 7, and that would mean that it's changing at negative 0.557 degrees Fahrenheit per hour. So from 3 p.m. to 9 p.m., my graph was, or my temperature was decreasing at about a half a degree per hour. Find a function of best fit, linear, quadratic, or cubic. Well, let's go ahead and do each of those and see which one looks to match. So let's start with linear. y1 is approximately m of x1 plus b. That doesn't look like it's very good. It doesn't hit very many of the data points, and they're pretty far away. And notice the r is 0.56, so it's not the best. So linear probably is not the best. Let's look at quadratic. So y1 is approximately ax1 squared, then plus bx1 plus c. Again, not the best. It doesn't look like it hits a lot of those blue points, and it's missing some. So let's hope that the cubic looks the best. So that would be y1, and then approximately ax1, cubed, and then plus bx1 squared, and then plus cx1, and then plus d. That looks to fit the data way better than either of the other ones. So I'm going to delete my, or undo my quadratic and my linear. So it's not perfect, but it seems to follow the data points the best. So my cubic function looks the best. So my cubic of best fit will be y equals, and then it would be negative 0.0079 x cubed plus 0.2929, so 29 x squared, and then minus 2.648 x, and then plus 47.6857. All right, so that looks to be my cubic of best fit. So it looks to be like a cubic is going to be the best one. Draw a scatter plot. Okay, interpret the y-intercept. So what does the y-intercept? So the y-intercept is when x is equal to 0. And we already talked about that. When x is equal to 0, we're at midnight. So the y-intercept would be the temperature at midnight. All right, so on our line of best fit, it's telling me that the temperature at midnight was 47.686 degrees. So that's what that means in this problem.